by Jim Head, and the title is Exploration of Planetary Crusts, a Human Robotic Exploration Design Reference Campaign to the Oriental Basin. Jim,
thank you, sir. Thank you very much. It's a great pleasure to be here and talk about way in the future, perhaps not too far in the future, a campaign. So what I'm going to talk about today is how we take what we know about the moon and really design an architecture which takes in human and robotic exploration and actually explores the relationships between those to optimize our understanding of the moon. So first of all, of course, the Apollo program, which I had the luck to be my first job out of school working in astronaut training, site selection, mission operations, we had a strategy for site selection. For example, we really wanted to understand what was going on in terms of the major features on the moon, their origin, their ages, their compositions, mineralogy, petrology, etc. So the first two missions, Apollo 11 and 12, went to different parts of the Maria and to determine their ages, their structure, etc., set up the chronology for the moon in general. And of course, Apollo 14 went to the Fra Formation, the ejecta deposit of the Imbrium Basin. This was a major baseline in the understanding of the stratigraphy of the moon. Apollo 15 was designed to go to, in fact, a basin ring, the Apennine Mountains of the Imbrium Basin, to look at the stratigraphy, to look at the structure, to get samples from deep within the moon, and indeed lunar crust, and then indeed to explore Hadley Rill and the Mare there to date that. Apollo 16, of course, went to the Central Highlands to look at plains, the origin of the plains there, etc., and the chronology of the highlands. And of course, Apollo 17 went to the older basin, Serenitatis, predating Imbrium, to look at the structure of that basin along the purported rim crest of the basin, as well as the dark mantling deposits. So we didn't know much about the moon then, but we do now, based on this and all the other exploration that's gone on. And in fact, over 40 years later, 42 I think exactly, we in fact convened a microsymposium in which we looked at the characteristics of the outstanding problems that we have today. So updating all these findings and thinking about, in fact, what the fundamental problems were for the future exploration of the moon. So in fact, we had a series of themes here, the outstanding questions, highly sharpened by our recent missions, Lunar Reconnaissance Orbiter, the GRAIL mission, and lots of other missions from international partners. What's the crustal geometry and physical structure, crustal chemistry, mineralogy and petrology, external crustal modification, looking at the impact record, how the impact record actually modifies the surface as well as the chronology, and of course the whole question of what are the major outstanding problems and how do we go about attacking them. So what we've done here, many of us, is to design discovery missions, new larger missions like we just heard, South Pole and sample return, to try to address individual aspects of these problems and collectively as many as we can. But what we've tried to do at Brown here as part of our survey activity is to look more broadly and design a campaign. If we were to go back, not necessarily to one place here, one place there, one place somewhere else, what would we do to have a campaign to address all of these questions at one time? And of course, the reason that we went to all these different places in the Apollo program was to get diversity, but also to optimize. Now we know a lot more and we can focus on specific areas. And of course, one of those areas that is really great on the moon for this is the Oriental Basin. You can see here, usually what happens is that we end up showing Rhode Island for scale, which is about the size of a bolide. It's not very impressive, but I like the idea of using Rhode Island to impact the surface and cover the state of Texas with the ejecta in the interior, so you can get some idea of scale with what's going on here. But the whole key point here is that the Oriental Basin is really fundamental in our understanding. It's the real paradigm for how we can get at a host of the problems that we're talking about out of the workshop for the microsymposium. So for example, we know that it has three basin rings, the Cordillera, the Atarook, and the Innerrook Mountains. We also know that the major ejecta deposits surround it, the Hevelius Formation, that impact melt coats the interior. Lunar Mare volcanism, secondary crust also modifies it, but not to the extent as the other basins. So that's why we can go in here and really look at the impact melt. In addition, there's this intervening facies, the Montes Rook Formation and Abi facies of uncertain origin. So this gives us an opportunity to study basin rings, to study basin deposits, pristine basin deposits, and we can learn a lot. So one of the major objectives is to understand the transition, indeed, from simple craters to complex craters to peak ring and multi-ring basins. And Orientale provides us this opportunity, really the baseline to look at this transition. We need to understand what's going on here in terms of the amount and role of impact melt and impact vapor, as well as the ejecta and its characteristics, and of course the transition from complex craters to peak ring basins, trying to understand which of these two rings corresponds to which rings in the Orientale Basin. We can take a look at those, for example, and try to assess these and the origin of these specific rings and the deposits that are intervening. And of course, the question is, which basin ring most closely corresponds to an estimate of the transient cavity? The transient cavity is transient, so it doesn't sit still and wait for you, but nonetheless, one of these is an estimation of the best estimation of what that is. So what is that question? How can we explore that with exploration of Orientale? The major additional objective is the nature of the crust. We know, for example, this is almost 10 years ago, that new views of the moon had a general paradigm for the structure of the lunar crust. Okay, is that still correct? We have a lot of data that's been obtained subsequently, and we know, for example, that there's some variations on this theme, but we heard today about the magma ocean model generally holding up. But how can we explore this in detail to really get at things? We heard a little question about, was the Apollo 16 samples, is that really representative? Well, here we can take a look at Orientale and, in fact, test these ideas. The moon mineralogy mapper data, unbelievable. We can actually know where to go, what to do, what kind of rocks to take, what kind of tests we can have about crustal structure, as well as the origin of these rings. Leah Cheek's work, for example, looking at the virtually pure anorthosites, 98% plagioclase, concentrated in the peak rings here. We can answer questions by exploring these to take a look at the characteristics of these different deposits. For example, what's the shock heterogeneity and homogeneity associated with these things? Are the plagioclase, large crystals that might have come from, the middle crustal evolution, cooling, etc.? These are all sitting there waiting for us to explore, and in fact, we know where to go. Any one of these dots in here, these red dots, would do it. So we also have evidence for 10 to 12, maybe 15 kilometer thick impact melt layer from this basin. Okay, so it's sitting there waiting to expose, waiting to be sampled in detail. There was approximately 1 million cubic kilometers, we estimate, of impact melt. Did it differentiate? Did it not differentiate? What does it look like? How do we relate this to the questions we saw earlier about the diversity of the materials in the crust? Secondary crust is also critical for Orientale. If you take a look here at perspective view on Orientale, Orientale does have mare deposits. They're just not abundant in the same sense as the other basins, but they in fact show some representative textures. If you take a look here at 1 second equals 100 million years and you watch this fill up, okay, that your lifetime is measured in nanoseconds here, just for perspective. But you can see at 1 second equals 100 million years that this thing is filling up over geological time, extensive geological time. It's not all coming up at once, flooding the basin from pressure release melting or anything like that. This gives us the opportunity in this Orientale campaign to actually sample all these basalts. And in fact, when we go to look at the characteristics of these, okay, what we find is that the perspective on all these basalts here, when we look at these ages, here's the ages in blue of the whole near side. Here's the ages of the Orientale ones. They actually span the complete age, pretty much, of what we see on the near side. So we can take a look at the evolution of all the basalt age range from exploring Orientale as well. So the bottom line is we have tried to develop this kind of perspective and structure by taking a look at a campaign, not just exactly, what's the next mission, but what do we do to actually take a look at a campaign and go after these things. And we have, in our context here, human robotic exploration optimization. We're looking at precursors, we're looking at context, we're looking at infrastructure operations to support long-term exploration, such as a GPS system sort of in orbit, etc. Interpolation, how do we use robotic missions to interpolate between human traverses, extrapolations, and progeny, by which we mean, what do we do after we go with humans to follow up on the findings that we have back in the lab? So the key point here is that we've been looking in our survey efforts, a Brown-MIT effort in our survey collaborations here, on science and engineering synergism. Apollo 15 Commander David Scott has been very active. He's a visiting professor at Brown helping out with this project. And indeed, we're working with the people at MIT, including 5-time shuttle astronaut and also Sasha Basilevsky, who is one of the robotic explorers from Lunokhod. He was in mission operations during that time. And we work with the students in what we call science and engineering synergism. So the idea is to put together an architecture to try to actually do this kind of exploration and optimize human exploration, but also human robotic exploration as well. So resuming human exploration of the moon. What approach, what architecture? That's the challenge the students in these classes are given. And they came up with an amazing, amazing common sense approach. The first thing was to say, well, geez, let's see, humans to the moon. Wait, we did that once, right? Apollo, I think it was called. So let's go back and take a look at Apollo 40 years later and see what we could do with that basic architecture to go back to the moon. Okay, so they looked at things like fuel cell technology, they looked at carbon composites, and actually went in and figured out what they could do with that architecture given 40 years of technology development. Amazing, okay? But first we sat down and we set the scientific requirements. We said, okay, look, don't tell us what you can do. We want to tell you what we need, okay? So being greedy scientists, of course, we asked for full lunar access, the poles near side, far side. We wanted longer stay time, 7 to 14 days. We wanted more payload, up mass and down mass, take experiments up, bring rocks back. We wanted more mobility on the moon, more flexibility with robots, and human-robotic partnerships. A tall order, but they really came up with some fundamental answers. So when all was said and done, they came up with this human architecture for lunar operations concept, which in fact took the basic Apollo architecture. And if you take a look here, payload mass for the LEM, they got 500 kilograms, 12 to 2,300 kilograms. Sample return mass, 100 kilograms for Apollo, 350 to 730 kilograms. Crew to the surface, 2. They got 3. Surface days, they went to options 7 to 14 days. So they really came through with this incredible architecture, okay? And it's actually quite affordable as well compared to, for example, what you see in the middle here, which is Constellation. So this is really an incredible thing. What we're trying to do here is optimize the engineering for science, keep it simple, start with what worked, Luna and Apollo, and use 40 years of technology development. But a key point here is that we're training the next generations as well. We developed a bottom-up approach, not a kind of a Constellation top-down approach. In fact, scientists and engineers were working really shoulder to shoulder and together. We're trying to help them make our scientific dreams a reality. And in fact, that really worked very, very well. So 3 minutes, wow, I'm proud. So let me just point out what in fact they did, okay? So we actually are designing traverses now using this Apollo architecture for the South Pole, for the Oriental Basin to do these long-term stays, 7 to 14-day stays, sortie missions to various places. We have 6 major landing regions, areas of interest, if you will, that we're looking at to try to solve all these problems that we outlined at the microsymposium, et cetera, in one major campaign of human and robotic exploration. Now, for example, one of the very imaginative things that the students did was to, in fact, they noticed that with Constellation here, Constellation would take their descent fuel tanks all the way to the surface, but it's a huge cost to do that. So you land with this huge thing of empty descent stage fuel tanks, and they very creatively came up with the idea of actually jettisoning those on the way down and saving a huge amount of mass to the surface and of excess mass that you don't need, and optimize this. And they came to us after one of our sessions and said, we have a problem here. We think we can take a lot more to the surface by doing this operation here of Lloyd separation and getting rid of this, but we're going to have to create a crater like about 4 kilometers away. Is that going to be a problem? We're going, oh my God, you're going to make a crater for us? So it's like, we could really use a crater, okay? So, we want to examine that. What does a fresh impact crater look like on the moon, freshly excavated, et cetera, et cetera? So this is the kind of science and engineering synergism. So that got built into the mission so that we can do things like this as well. So the bottom line is we have a whole set of these things that we're looking to optimize. We have 6 landing sites. Let me just point out here in the interest of time an example of the Inner Rook Peak Ring Massifs. So here is just a chart showing the region of interest of this, okay? So here's the Oriental Basin. Here's this block here. You can see in a cross-section we would land in this region here in the Peak Ring Plateau, which has the Peak Ring draped with impact melt. We think we can land sufficiently close so we can also get to the Outer Rook Ring, and we would surely be sampling these plagioclase, very plagioclase-rich deposits that Leah Cheek and her colleagues mapped out. So this is just one example, and I would say, for example, we also are using for the other areas of interest our previous missions to Apollo 17 and 15 landed in analogous places at the REM and the Cordillera Ring on other basins on the moon. So this has all been really important. I think, who knows when this will happen, but I think it's important to have an integrated architecture that, for example, says, how do we solve all these problems by focusing in on an area based on our Apollo experience, et cetera. So that's what we're doing right now. Who knows when it will happen? Maybe President-elect Trump will want to have Trump Towers on the moon. I mean, who knows? But we'll be ready when the time comes. Thank you very much.
We have time for one quick question. If somebody wants to ask something. If not, I'll take the chair's prerogative and ask the question, how applicable is that architecture to other places?
Well, I mean, the whole idea is to develop a human-robotic partnership and precursor